Before we revisit the graphical method, we will prepare ourselves with some other concepts. So in this mini lecture, we will learn the pressure coefficient on the small disturbance assumption, which means how do we calculate the coefficient if we apply the small disturbance assumption? Okay. We know this pressure coefficient already, and it has been done in the previous mini lecture. And now we are considering isentropic process. Then we have this relation, which is a relation between the pressure ratio and the temperature ratio. This P and T are the pressure and the temperature at a random point, for example, over the aerofoil. Okay, and also we are including the energy equation. On the left-hand side is the total entropy at a random point over the airfoil, and the right-hand side is the total entropy of the free stream. And because of energy conservation, they are the same. And now we just do some manipulation, put the temperature on the left-hand side and the velocity on the right-hand side. Okay, so now we are dividing, both sides are divided by the free stream temperature. So we have this, and then because gamma RT is velocity sonic speed square, so we just replace gamma RT by A infinity square. So we have this ratio. Okay. Now we are applying the perturbation velocity. Do you remember the small perturbation assumption? Okay, the free stream, the streamwise velocity is u infinity plus u prime, and the vertical speed of normal speed is v prime. So now we are just replacing u squared by this portion highlighted by the red. Okay, so now the pressure temperature ratio can be expressed by this way. Okay, so now we have the temperature ratio, and just put it back to the isentropic process, which is a relation between pressure ratio and temperature ratio. So we have this relation. It looks not so neat, but let's see what happens next if we are further applying the small perturbation assumption. Okay. Since we are looking at the pressure coefficient and we've derived the coefficient, how it was expressed by the velocity perturbations. Now we can rewrite the pressure ratio as 1 minus epsilon to the power of gamma divided by gamma minus 1. In here, epsilon is a small number. Okay, so now we are applying the binomial expansion. If it's a plus b to the power of n, and then on the right hand side this relation can be expanded like this way. And similarly, we can apply the binomial expansion towards the pressure ratio. So it is done this way. And because Kc, as it was assumed, it's a small number, so epsilon square is smaller, far smaller than epsilon. So from the certain onwards, they are all smaller than epsilon, so they can be cancelled. And then the pressure ratio is equals 1 minus gamma divided by gamma minus 1 epsilon. So this is how we progress. And let's see what happens later. And because earlier we have this, and that's a pressure ratio, 1 minus something, a big 10 to the power of gamma divided by gamma minus 1. Okay, comparing the two equations, we can find the highlighted part by blue is actually equivalent to epsilon. And then we can have P over P infinity equals 1 minus that highlighted part. And now we are using the small disturbance assumption because u prime square plus v prime square is far smaller than U infinity square. So the second term in the bracket can be eliminated, and then the pressure ratio is 1 minus gamma m infinity square times U prime divided by U infinity. So this is a final relation of pressure ratio by using the small disturbance assumption. Okay, now we have the pressure coefficient and the pressure ratio, and we just replace the pressure ratio in Cp by the actual pressure ratio, and then we can find Cp equals minus 2U prime divided by U infinity. So this is a very neat relation, but we need to remember it was derived on a small disturbance assumption. So you can see now we get the pressure ratio. Why? You may wonder why we need pressure ratio, and we'll see the answer later.